once again let me continue to your previous lecture what we are discussing. That was basically steps in foundation design. These are of course qualitative steps, actual step we have not discussed yet. These are all qualitative. What we have to do, that I am giving you some idea, and we have examined most of the steps. Now, I will last steps actually perhaps left, and that I will discuss. Let me go to the next slide, and you can see that I have listed right from beginning, actually from 6th lecture onwards, and I have discussed one by one these all those things I have discussed. Now, this is the one monitor design, construction and performance, and basically based on so many observation and inspection, some report will be submitted, and then based on that report actual design will be there. So, while designing also one has to have some monitoring, and also during construction also should have monitoring. Also after construction also, when it will be in the open for service, and there also you have to have some monitoring. Why the monitoring is necessary? Because we have designed with some expectation that it will perform like this, but it may not perform accordingly. In that case actually it may not perform. So, may or may not. So, that to make sure that you have to have some monitoring arrangement, and you have to see that it is performing properly, and if it does not perform, then obviously you have to do some corrective measure even after construction also. So, these are all finally in the form of summary. I will of this whatever we have discussed, I will see in the next two slides. You can see under this monitor design, construction and performance, in the, and together I can say the summary of this entire 2-3 lecture I will just put together. And that foundation design is just assessing all your options through analysis and choosing the best one, is not. So, as I have mentioned that you may have different site condition, you may have different soil properties, you may have different loading condition, and you may have different contractors, different material availability, all those things to be considered, and then finally, you may have several options, and finally, you have to choose the best one. So, that is what foundation is just assessing all your options through analysis and finally, choosing the best one. And for this actually you requires to understand the site and project and ability to consider what might go wrong. That means, while doing all those things and while taking several options, you need to know that if I do, what is the benefit, and if I do, what is the harmful or difficulties. So, in that like that for each options you need to know that sometime some option you may have 9 or 10 positive points and 2 negative points, and there may be some aspect alternative, there may be 50-50. So, you have to choose accordingly which one give you best benefit. So, that is the one you have to understand. Until you understand entire site and project, then you will not be able to judge this one. So, you have to what might go wrong based on certain selection, that also you have to visualize. So, this is another point, and this also I have told again and again that soil mechanics is a tool that will help to select and design, construct foundation elements and earth structure. That means, whatever foundation design, that means whether it is a earth pressure, earth retaining structure, whether it is a pile foundation, whether it is a shallow foundation, whether it is a some other type of foundation, wherever you do, ultimately you have to apply soil mechanics. So, that is what the soil mechanics, first of all you have to digest properly. Until unless you do that, then you will not be able to become a successful foundation engineer. So, these are the things to be noted. Next part is that this is very important. You can see the failure is an unacceptable difference between expected and observed behavior. That means, you have designed something, we expect something it will perform this way, and after construction whatever observed, the difference whatever expected and whatever observed, if they are same, that is a successful design. But whatever expected and whatever you are observing, they differ too much, that means a failure. And this is that means it is not always is failure, and that difference become unacceptable. That means, if settlement is kept suppose 25 millimeter and settlement after 50 millimeter is not stopping, that means it is beyond our acceptable limit, that means that considered as a failure. That is what failure is, an unacceptable difference between expected and observed behavior, and this failure should not occur actually. Once you construct something facility for some purpose, then that should not fail. So, that is our expectation. So, if it fails actually you have to know the consequences of that, and so because of that you have to take extra precaution to make sure that foundation is sound and serviceable. So, that is the one part to be kept in mind. Key goal as foundation engineer, build economic foundation that works. That is what I have mentioned few minutes back also, or in the last lecture in fact, that you have to do several analysis and you have to do several investigation, but finally you have to design or build something which will work. That means, if the design comes 1 meter, but I adopt something 1.5 meter, there may be some insight I have that 1 meter may not work, though it is giving you from the design that it is giving 1 meter, but still I will adopt 1.5 meter or 1.25 meter, my insight actually will not permit 1 meter. So, these are the things actually, that means with experience you will gain this, that key goal as a foundation engineer, build economic foundation that works, that means safe and serviceable. That means, sometime based on design etc., you may get a value, but you may adopt something else, because considering the safety of the system, you from your experience you may feel that that is not correct, though you are getting from the analysis, but that may be something else to be adopted. So, that is also to be developed over time, not by one day. Build with confidence, that is what that means. Use field work, lab result, analysis and design, but at the end use what work. That is what whatever I have told you, that you do analysis, investigation, ultimately so many things, but finally you have to adopt something which will work. And sometime use rules of thumb when possible to check for reasonableness. That means, what is the meaning of it? That means, there are thumb rules in particularly civil engineering, in the field people actually know what should be the minimum size or minimum number, this is known very well. So, though based on calculation you are getting certain values, so by thumb rule actually you have to cross check that whatever it is there, it is workable. For example, this reasonableness is very important. Most of the time while teaching we have seen that because of the some software, many people are nowadays using the software for design purposes, and that software actually adopt certain units, and our soil parameter or material parameters also have a definite unit. Ultimately, if you do not give the input compatible to the what software is taking, then your result will be something, and sometime it is 200 millimeter or 200 centimeter or 200 meter. Sometime most of the many a time students are not able to judge, and it happens many a time that the depth of the foundation, some students are coming suppose 2 meter or 2.5 meter or even 3 meter or 4 meter, but they do not know whether this 4 meter depth of the beam is generally not possible for the building, because building height is maximum 2.5 to 3 meter around 10 feet. So, that means that reasonableness, that means you have to judge by some means that whatever result you have got is reasonable, that somehow by some means you have to check, and that is in the field actually, particularly in civil engineering there are many thumb rules available by which one can make sure that whatever you are constructing they are acceptable. Next actually I will enter slowly now foundation engineering really. So far we have given introduction actually, that means what are the steps, and those steps really is not a design step, they are all qualitative steps. What you have to, how you will proceed, that I have mentioned. Now, really I am entering to foundation engineering, and this foundation engineering, when you enter, the first thing I need to classify the foundation type. That one actually when you broadly classify, it will come two groups, one is shallow foundation and another is deep foundation, and this is already in the introduction time partly I have covered. And shallow foundation generally less expensive and better for lighter structure on less problematic soil, and that means if the problematic soil will not be able to do that. That is what that shallow foundation is applicable only less problematic soil or even no problematic soil, and your cost is obviously less, and foundation is generally at shallow depth, and typical types spread footings and raft mat, that also I have given example in the previous lecture. I have shown the photo sketch also. And deep foundation actually obviously it is, I have also mentioned already, that is more expensive and typically used for heavy and tall structure, So, maybe at end can be a heavy and tall structure on more problematic soil. Not only that, heavy and tall, and even when there is a soil is problematic, sometime pile foundation is the solution or deep foundation is the solution. So, problem, and typical type of deep foundation is driven piles, drill piers, and sometime caisson and well foundation also comes under deep foundation. This is deep foundation, already I have shown once, actually is more expensive and used to get acceptable bearing capacity and settlement. That means, if I build a shallow foundation for this building, then whatever pressure comes to the soil, that may exceed the bearing capacity of the actual soil. So, because of that, that is one thing, that to achieve acceptable bearing capacity, that means you have to, the long structure like this, you have to drive inside the soil, and when you drive this structure, then it will have friction along this surface, then maybe the tip, there may be the resistance, all those together, and if it is a large number of them are there, then whatever capacity it gets, it may be the enough to support the entire building load. So, that is why they used to get acceptable bearing capacity. Another reason why you go for deep foundation, sometime if I adopt a shallow foundation such as building, then you may see that the settlement of this building may be significantly high, which is not permissible. In that case, by adopting deep foundation, we can restrict those settlement also, and typically used for larger structure on more problematic soil, that already I have mentioned. And you can see shallow foundation, the definition, it is not a qualitative definition only. A shallow foundation transmit the structural loads to the soil strata at a relatively shallow depth, and most of the shallow foundation will be within 1 to 2 meters, even less than 1 meter also possible. And as Terzaghi gave a guideline as an approximate criteria as per Terzaghi definition, that shallow foundation is one which is laid at a depth df, that is, if this is the foundation, if this is the foundation and this is the ground surface, then this is called depth of foundation df. If the foundation is laid at a depth df and which will not exceed the width of the footing, that means, if this is B, this is BF. So, DF over BF, it will be less than equal to 1. So, according to Terzaghi given definition, that the shallow foundation, that means your foundation will be laid at a depth df in such a way that it will not exceed the width of the footing, then that soil, that one will be treated as shallow foundation, and if it is exceeds around 15, then that is called deep foundation, and in between called moderate depth foundation. And most of the foundation, whatever I have mentioned, that isolated footing, steep footing, raft footing, combined footing, all are actually depth vary between 1 to 2 meter absolute depth, you can say, and really that is shallow depth. And if I give a general guideline, that is actually df by b less than equal to 1. And you can see that that isolated footing, this is a plan view, this is the elevation, that means this is a footing and this is the column, and when you do the analysis, then what will happen when footing will be there, below the footing there will be earth pressure, there will be pressure given by the soil. Because of the load in the column, the soil will be resist that load, that pressure will be there, and if for the analysis purpose we will take this foundation like this, it will be a one point and it will be two. This is the member, like you can assume that the beam is hold here and this portion is cantilever with a loading downward. So, accordingly this member can be designed. So, this is the footing, plan and elevation, and this is the idealization for analysis. And this is called isolated footing, sometimes it is called spread footing, sometimes it is called pad footing, as I have told before. And these are all other type of foundation. You can see that this is the one, as I have told you, combined footing, this is the elevation and this is the top view. And this sometime the if your, because of various reason, if the column does not carry equal load, that means then sometime your foundation may be something like this also, trapezoidal also. So, combined footing, not only that it will be rectangle, it can be of other side or shape also. And this is the one, that is strip footing, that is a elevation, and this is the front plan view, that means this is the wall thickness and this is the width of the footing, and this is actually thickness of the footing, and this is the wall continuation elevation we are seeing, and this is the side view, that means from the side, if you see from this side, you will say footing like this. And then there is a, this is called sometime called strap footing. Strap footing is actually basically these two footings are isolated, but because of some reason, unequal load and many other reason, these two also will be connected by beam like structure. So, that some load, some balancing of load will be there. So, that is actually called strap footing. This is also a special type of combined footing. And as I have mentioned before, that when many of the footings are connected by a single foundation, that is like this, you can see these are the foundation plan, and there may be another footing here also, column here. So, all will have a common foundation, that is like if you see this side view, isometric view, you see like this, and elevation and plan is like this. So, that is called raft or mat foundation. So, this is combined footing, this one, both are combined footing, strip or continuous footing, this one, strap footing, this one, a raft or mat foundation, this one. And now, actually when you will apply a load through a footing, suppose there is a footing and if you apply load through this on the soil, suppose if I apply load, then if I observe load versus settlement, then you will see load versus settlement, you will get a plot like this. Not always, there are different types of plots are available, and if the soil is having general shear, that means the footing is loaded here, then it is also experimentally shown that the below the footing soil will be having like this 3 distinct zone 1, 2 and 3, and there will be some little bit of heaving at the surface, and with the increase of the load, the within the soil this will happen, and if you record load corresponding to settlement and if you plot, then you will get like this. and what will happen that it will reach to a peak, and then it will be suddenly will give you large settlement without increase any load, that means that is failed, soil failed, and this type of failure is called general shear failure. And the load at which that shear failure occurred, that is called actually ultimate load, and if it is converted into pressure, that is ultimate pressure. The maximum gross intensity of loading that the soil can support before it fails in shear is called the ultimate bearing capacity or QU. Okay. So, that means, if I when the soil just fail, just before the failure, whatever the pressure is here, that is actually ultimate bearing capacity. Now, if this is the when load versus settlement, if you see like this, then that is called general shear, that is mentioned by Terzaghi. Then similarly, in some soil, if I load and then below the foundation, you may have like this, that means these two zone will be distinct, but this zone somehow will not be distinct, this failure surface will not reach up to the ground surface, and this weaving also at the surface will be broken. And when you will be record the load versus settlement, then you will see that it will go almost straight line, suddenly reach a peak, and again it will change the slope another, that means the number of failures will happen. So, like that you will get, then again it will be broken line, it will continue like this. So, number of you will get a curve like this, you will not get a typical curve like this. Instead of that, you will reach a peak on point, then suddenly it will be reducing, load will increase, but not at the same rate, it will lesser rate with settlement or more settlement with less load. So, that way will happen, then finally will be happening. So, this type of phenomena when you observe, then that is called local shear. And another type of soil when it will be actually overloading, when there will be 3 zones like this, it will not form and suddenly it will punch to the soil, that is called punching shear. And when you will find out the load settlement curve, then you will not get any peak, no such peak you will get, continuously it will settle, and that is called punching shear. So, that means, when the soil is loaded through a footing, then soil can fail in different ways. One, it can be failed by general shear, it can fail by local shear, it can fail by punching. Okay. And again this depends on some of the factors, like what soil will fail in general shear, what soil will fail in local shear, what soil will fail in punching shear. There are some guidelines, actually there are some investigation are carried out, and through the relative density of the soil, this is actually clarified. The relative density again is a part of soil mechanics we have discussed. The relative density dr actually relative density dr actually E max minus E divided by E max minus E minimum, that void ratio, maximum or minimum void ratio and in situ void ratio if you know, then by doing this calculation we get a number that is actually relative density in percent. And you can see relative density plotted in this axis 0.2, 0.4, 0.6, 0.8, means it is 20%, 40%, 60%, 80%, 100%, and this side actually df by b. And you can see that if the soil relative density become more than 35%, the soil relative density is less than 30%, it is expected that punching shear will fall, because the entire zone is punching shear. And if it is 35 to up to suppose 70, the soil with shallow depth may have local shear, but when depth is increasing, then they may have of course, this is the zone actually where actually depth df by b and relative density vary in such a way. This is the zone, if the soil comes, then that soil will have local shear, and if the relative density is more than 70% and df by b in such that it vary between this, then entire zone will have the entire that means the df by b is set in such a way and relative density is more than 70%, then you will have the all soil will have undergo general shear failure. So, that means though your relative density is 80% and dF by B suppose 4, though very dense soil, but still because of the depth that soil may undergo failure by local shear. Most of the time good soil, good dense soil will have general shear failure, but it has of some relationship with depth also. If the depth of B suppose is very high like 4 or 3, then there is a chance of local shear failure also. Okay. So, these are actually otherwise you can see the relative density up to this means it is all punching shear, from here to here this is actually, and if it is a shallow depth between 1, most of the time your shallow foundation is dF by B is 1 or in between. So, if it, that means if it I put like this, then when relative density is less than 35, then you will have local shear. If relative density is 35 to 70, then you will have local shear, and 35 to 100% you will have general shear failure. Now, this is actually finally, it is observed general shear failure is considered and it is modeled, and then bearing capacity theory can be developed, that is actually given by Terzaghi, that he has assumed certain things, that soil is homogeneous, isotropic and all, and then several other assumptions like water table is at a great depth, and based on that assumption he has given this model. And if you see that there are 3 distinct zones, that is, this is called wedge zone or static elastic equilibrium zone, and this is called radial shear zone, and this is called Rankine passive zone. And here actually as per Terzaghi suggested that this angle supposed to be phi and this angle supposed to be 45 minus pi by 2, and when we apply the load and then ultimately until unless this wedge goes downward, then soil will not fail. So, that is the one actually main thing, this become actually part of the foundation, this wedge become part of the foundation, and if I consider equilibrium of the wedge finally, then before failure there will be a cohesion suppose, there will be reaction from here suppose, and there will be loading suppose here, and there will be weight of the soil, weight of the soil, these are the things will be there. And if I consider the equilibrium, vertical equilibrium, then this component I will take in this direction, this component I will take in this direction, plus this into this, this plus vertical component of this, vertical component of this, all summation minus weight should be equal to this. And if I do this, then finally we will be able to express bearing capacity into 3 components, and that 3 components, one is called cohesion component, another is called surcharge component, another called density component, and those 3 components will have 3 factors, and they are called bearing capacity factor, and one is cohesion factor. Cohesion related factor is actually NC, that means bearing capacity factor for cohesion is NC. Similarly, that surcharge factor NQ, that means bearing capacity factor for surcharge, that is NQ, and third one N gamma, which is actually bearing capacity factor for density. So, those things can be so like that I will continue in the next class with this, that I will take this wedge and finally, I will consider the equilibrium of this wedge, and I will calculate this force, I will calculate this force, I will calculate this force, and then I find out the weight of the soil here, and then I will consider the vertical equilibrium of this entire system, and from there I will express the bearing capacity equation in terms of N C, N Q, N gamma, and that is the thing which we have to finally use in the design, and perhaps I can discuss this one elaborately in the next class. With this I will close here. Thank you.